Yep. Bafika boy bini. Same time boy.
Yeah, right.
All right. Morning. Hi. So I see it's almost 8. I think it's 8 on the dot. So we'll start. Just quickly wanted to start off by. Can you hear me, by the way?
Yes.
Okay. Right, thanks. Just quickly wanted to start off by ironing out a few things. There's a discussion. There's a question from one of you with regards to direct memory access, and it was really tied to the sequence of events here. And I stalled a little because I was a bit uncertain as to how exactly the signals are sent through to and from the CPU. But the best way of understanding this is by appreciating the fundamentals associated with DMA. You know, the fact that the technique in itself provides direct access to memory, right? So rather than go through the CPU, the peripheral will have direct access to memory. And so the idea behind this is you have the DMA controller, which will ideally temporarily gain access to the address bus. Address bus that is ideally going to be mapped onto the address in memory where data needs to be transmitted to and data needs to be read from. When we had made mention of the fact that the peripheral will send a DMA request to the DMA controller, what we're saying is it needs to signal the fact that it needs access to memory. And then what the DMA controller will do is it will tell the CPU that it needs, or the peripheral needs, temporal access to the address bus so that data is transmitted to and from the memory. Right? So that would be the hold request. Essentially, you're requesting to temporarily gain access to the address bus. Right? And then the CPU will send an acknowledgement to say this is fine, you can go ahead and do that. And then boom, the DMA controller will now have access to the address bus, and then data can be transmitted to and from main memory. So the idea really here is to send a request to the CPU so that you gain access to the address bus. What you're interested in is memory. Before you can gain access to main memory, you have to signal to the CPU that you need to gain access to main memory. Something else that you probably have figured out by now is that you have noticed that this would typically be the case for devices that transmit large volumes of data, right? So things like your internal hard disk, for instance. I hope this helps clear out things. I can't remember who exactly asked this question, but I'll just pause for a little while to find out if this helped iron out a few uncertainties that were previously there.
Oh, yes, I thank you very much.
Okay.
So Mr. Lighton, you mean that the access is not direct, but it's usually sends signals, eh?
Yeah, well, so the peripheral, ideally, with direct memory access, you have access to main memory. But before you can gain access to main memory, you have to tell the CPU that you need access to main memory. Which is why the first thing that happens is the DMA controller will issue a hold request to the CPU. So the answer is yes. Before you can actually gain access to main memory, you have to request for access to main memory. This raises a number of interesting things, because you notice that the only interaction, that the only part where the CPU comes into play is when a request is being sent through to the CPU by the DMA controller to say, I want access to main memory. And then afterwards, boom, the CPU continues with whatever it was doing, and then the DMA controller takes over, essentially. All right. And then we started off our discussion of so-called memory. We started off with an overview. And today we're supposed to transition and start discussing the various types of primary memory. But in terms of the recap, I just wanted to remind us that the idea behind main memory is tied to the so-called stored program concept. I hope we still remember this. The fact that you have data and instructions located in this one space called memory, and then the CPU will be able to gain access to the program instructions and data, right? So in all these discussions that we're going to go through, whether we are making reference to cache, RAM, ROM, or registers, fundamentally what we're looking at, what we're discussing are structures that will hold these program instructions. The difference that might arise would be differences to do with how much of those program instructions and data being held by these various memory components. So in the case of RAM, you typically have the entire program, or at least portions of the program, being loaded into RAM. When you're making reference to things like cache, for instance, and registers, what you're holding, what you're making reference to is just individual instructions, right? But fundamentally, it's program instructions and data, right? And in our discussion, in our overview of memory, we also looked at various aspects that help us better understand the differences that exist between these different memory components. And we realized that these are best viewed from the perspective of how fast these components are, how much of data and instructions they can hold, and their relative cost, essentially. You notice that the behavior of these different aspects kind of like varies depending on which particular component we're making reference to. We realize really that things like the speed will tend to decrease as you're moving away from the CPU. The capacity also increases. This is obvious, obviously. You just have to be logical for you to appreciate this. And the cost also decreases because of the technology that is used to implement some of these components. And then we introduce this pyramid of sorts, right? Which incidentally encompasses everything. So both primary memory and secondary memory. We realize that the behavior is more or less the same when you incorporate secondary memory as well. So as you're moving down the pyramid here, you notice that capacity increases, speed decreases, obviously, the cost will decrease. We introduce something that's going to come up again, this idea of whether or not a particular memory component is volatile or non-volatile, whether the data and instructions that are stored in that particular component are persistent or not persistent. We realize that as we're moving down this pyramid, you retain the contents of that particular memory component, irrespective of whether or not power is switched on as you're moving down the hierarchy. This is mostly applicable to secondary storage, right? But for primary memory components, for you to gain access to the data or the instructions, you need to ensure that there's a constant supply of power, right? So this idea of non-volatile and volatile memory, it will come back again. And so we did mention that our focus for this particular lecture series, or at least insofar as primary memory is concerned, is the top layer of the pyramid. And you notice that the top layer here, in all instances, you need a constant supply of power, right? And you're, for the most part, at least generally making reference to relatively faster memory stores. So registers, CPU cache, RAM, ROM. We also, right, we had a very, now these are just rough estimates. This is by no means exact, but just trying to give you an idea of how these different traits or aspects tend to change. What I think would be interesting, so the speed part and the capacity is pretty much obvious, but what I thought I would emphasize here is this idea of cost, right? When we're saying per unit size here, the best way of thinking about this is if you were to look at a unit size which is equivalent of 1 megabyte, for instance, this is just a rough estimate here, but what we're saying is that a 1 megabyte, one megabyte of cache would cost you this much. 1 megabyte of RAM would be this, which is like roughly a fourth of how much cache would cost you. The storage is even much, much cheaper, right? So we're saying, given a unit size of memory, it could be a gigabyte, could be a megabyte, a kilobyte. What we're saying is that the closer you are, the closer the memory component is to the CPU, the more expensive that unit size is. Right? Again, this is just a rough estimate, but you can do a quick check. Actually, I don't know how many of you have in the most recent past purchased, let's say, RAM and maybe an external hard disk or something. Best way to do this is if you have purchased RAM, let's say you purchase 2 GB of RAM, just come up with a hypothetical unit. Let's say, try and see if you can figure out the cost of 1 megabyte of that 2 GB RAM. Compare it against the equivalent cost of 1 megabyte of whatever external hard disk that you purchase. You notice that the cost of the hard disk is going to be magnitudes lower than RAM, right? Just a simple quick check you can do just to confirm this, right? And the interesting thing is that storage is actually becoming cheaper every year, actually. All right, I hope this is making sense. So we are going to immediately transition to start our discussion of these various memory components, right? Unless if there are any questions so far with regards to what we looked at, was it yesterday or the day before yesterday? Overview of memory, essentially. No.
Not yet, sir.
Okay, great. So, so the idea behind primary memory for the most part is to be located much, much closer to the CPU, right? For obvious reasons. Remember that the CPU, fundamentally the CPU is there to execute instructions, and the instructions that are executed are initially fetched from primary memory. So to ensure that the access to the instructions and the data is as fast as possible, the vast majority of these primary memory components are usually located much, much closer to the CPU. And I guess it's with the exception of so-called virtual memory, which is usually carved out from secondary storage. Right, so again, primary memory will provide the CPU with a staging area, right, from where execution of program instructions actually takes place or is initiated from. And so fundamentally, primary memory is there to act as a storage location for program instructions that are currently being executed, right? So this is where programs are initially loaded when you double click them or when you launch them. But we know that program instructions don't work in isolation. Typically, when you're using software, what you're doing, either explicitly or implicitly, is you're manipulating data. So primary storage also holds the data on which the program instructions will act. And again, so this is linked to the so-called storage program concept. Yes, sir.
When you're using VirtualBox, do the programs, the operating system, do they get loaded into memory as application software, or they just get loaded as same as the operating system?
No, so when you look at VirtualBox here, I mean, things kind of like change, right? So as far as your host operating system is concerned, VirtualBox comprises of the program instructions that ISO that you are acting on using VirtualBox is the data. But when you look at what's happening from the perspective of the guest operating system, completely changes here, right? Because as far as the guest operating system is concerned, it has no idea that it's running within an existing operating system. So the ISO image that you have that you've set up within VirtualBox would be viewed as data, and VirtualBox itself would be the program instruction. I don't know if this makes sense. But there's two different things here, right? Looking at what you just asked from the perspective of the guest operating system and from the perspective of the host operating system. Is this making sense, or are you confused or something?
I'll do a little bit of digging, but so far so good.
Yeah, well, let's clarify this. At least we have the question appear in the exam, and people get confused here. I think it's an interesting question. Which part is a bit unclear for you?
How is it loaded? How does it work exactly? Is it also treated like the way we treat VOC? Is it just loaded part-time? Certain parts of the operating system is loaded, or the whole operating system, so that it can be used the way it is used as a main operating system?
Yeah, but this is the thing here. But from what perspective? Is it from the perspective of the host operating system, or is your question from the perspective of the guest operating system? Because if you're looking at it from the perspective of the guest operating system, it's the same exact thing that happens when you're running the native operating system, where only portions of it is going to be loaded, right? Most important parts, like the kernel, for instance, it has to be loaded completely into main memory. But because the operating system is large, you only load part of it. So from the perspective of the guest operating system, only portions of that operating system are going to be loaded into memory, right? From the perspective of...
Yes, I'm talking about... Yes. The main operating system, sir.
Yeah, well, so from the perspective of the main operating system, what's going to be loaded here is program instructions associated with the virtualization software, in this case, VirtualBox. So whether or not it's the entire the whole lot of the software application that's going to be loaded into RAM is dependent on how many applications you're running at that point in time, and how much RAM you have. And even more importantly, how that piece of software was designed, right? So if I have a number of, and I don't know if you've run into this, if you have a lot of applications running at any given point in time, and you want to, let's say, run VirtualBox, and perhaps the amount of RAM that you have available is not sufficient, I'm sure you'll get some sort of error to say you have insufficient memory. This is very common on Windows, I think. Right, where you get a message to say you don't have enough memory or something. So it's dependent, so many different things. Number one is dependent on how much RAM you have, how the piece of software was implemented, right? Whether for the software to execute successfully, if the entire application needs to be loaded into RAM or just portions of it. I hope that makes sense.
Yes, sir. Yes, sir. Thank you very much.
Right. So program and data, right? So primary storage acts as a storage location for program and data. Again, this is tied to the stored program concept. But also, we want to emphasize or underscore the fact that the operating system, or at least portions of the operating system, are also stored into main memory, right? And we know this, that immediately after the bootstrapping process, the portions of the operating system are actually loaded into main memory, right? Again, memory size is usually measured either in, it's in bytes here, but usually in a human readable form like megabytes or gigabytes, right? We haven't gotten to a stage where we have, at least when you're dealing with more mainstream computers like microcomputers, we haven't gotten to a stage where you'd start dealing with terabytes of RAM, for instance, right? So usually you'd represent RAM in, let's say, gigabytes or something. When I was a student myself, we used to work on, I remember working on computers in the lab that had, I think it must have been 250 megabytes of RAM or something, right? And we used to get by. Those were crazy times, actually. Times when we would frequently make use of 1.44 megabyte sized floppy disks, right? But fast forward, I guess a decade, a couple of years later, and we now have instances where people have access to gigabytes of storage space, which is quite interesting, actually. Right. So specific types of primary memory, right, is registers, so-called CPU cache, random access memory, read-only memory, and so-called virtual memory. And we're going to discuss these in succession here. I wanted to start out by mentioning that this idea of cache will normally manifest itself elsewhere. So there's usually so-called cache that is made reference to when you're dealing with secondary storage. You probably have come across this maybe on your Android-powered devices, right? So there is also this cache. So you want to distinguish CPU cache from those types of cache memory, right? It's the idea of cache is just a technique used to temporarily store something for quick access, right? But our reference here is specific to CPU cache. Right? So the idea behind CPU cache is it's there to complement RAM, right? Remember that the idea behind the CPU is to execute instructions. And what you want is for the CPU to be able to execute instructions as quickly as possible. Because the CPU needs to fetch the instructions from main memory, one way of avoiding the latency that exists when the CPU needs to go to make a round trip to go and fetch instructions from main memory is to cache or to temporarily store program instructions and data that are frequently accessed onto the CPU chip itself. So this is why you have CPU cache. So anything that's cached, any instruction or data that's cached in the CPU will make it possible for the CPU to just avoid going to main memory to go and fetch whatever is in the CPU cache. So you notice a couple of slides from now that that in fact the first thing that the CPU does is when it needs to access instructions, right? Remember the fetch, decode, execute cycle. The first thing it will do is it will check if the instruction it needs to fetch or the data it needs to access is in either one of the caches. If it's there, then it will fetch it from there and then just execute it. If it's not there, then it has to make the long round trip to main memory and fetch it from there. Right. And then we have the famous RAM, which essentially just stores program instructions associated with software that are currently loaded into main memory. Right. We have a variation of RAM, which is read-only memory, plays the same role. The only difference here is that you only read from this memory structure, right? So you can't write to it, essentially. Now, this idea of you being unable to write to it is a bit hazy here because we'll soon see that that in fact there are certain variations of read-only memory, like erasable or programmable read-only memory or erasable programmable read-only memory, which in fact allows you to write to it, right? So modern day BIOSes would typically be EEPROM based, right? Where you can actually update the firmware that's sitting on the BIOS itself. If you have one of these modern laptops or desktop computers, I'm sure as you've been poking around the BIOS, I'm sure you've probably come up with an option where you can upgrade, right, or update the firmware itself. They don't normally advise you to do that, but if you know what you're doing, you can do that. Right? And then there's also so-called virtual memory, right? Because RAM is expensive. There's a technique that you can use to convert portions of your existing cheaper secondary storage so that it's viewed by the operating system as being part of RAM. And so if you have a computer that has, let's say, 1 GB RAM, and you know that you're going to be running certain applications that require significantly more RAM, what you do is you convert portions of the your hard disk, in this case, so that your operating system will perceive the computer as being composed of RAM that is slightly larger than 1 GB, right? Which is why it's called virtual, because it's not forced. It's not, I'm sorry, it's not true. It's not actual RAM, right? It provides the illusion of your secondary storage being a part of RAM. Now, it raises interesting questions here, or interesting things here. Like, for instance, just because you convert portions of your secondary storage doesn't necessarily mean that that portion of secondary storage is going to be much faster. No, it's going to operate at that same slower rate, right? You're just complementing existing RAM so that your computer appears to have slightly more RAM than it actually has. I hope that makes sense. So a couple of interesting characteristics associated with RAM here, or with primary memory here, is issues to do with, number one, the specific types of or categories of so-called RAM, and this is mostly tied to the different memory components that we have here, right? And by the way, this distinction, whether RAM is static or dynamic, plays into the cost aspect, right? So static RAM is essentially RAM that retain the data bits into memory as long as the power is being supplied to it, right? Dynamic RAM, on the other hand, does not retain the data, right? It's to do with the technology associated with how static RAM, for instance, is implemented, right? So in the case of dynamic RAM, or in the case of, I'm confusing the two here. In the case of static RAM, I hope it is static RAM. I think it is static RAM. In the case of static RAM, the idea behind ensuring that there's a constant supply of power is because the capacitors, right? The capacitors that are associated with the memory itself will usually lose their charge. And so you want to ensure that there's a constant supply of power so that they maintain that charge. Dynamic RAM, on the other hand, doesn't necessarily require you to supply electricity constantly, right? So it can maintain data that's located within it. And interestingly enough, actually, I hope I'm right here, but SRAM is normally associated with the actual RAM that we use, right? The stuff that is used to hold the entire program as you're executing it. And dynamic RAM is usually associated with the much faster memory components that are located on the CPU. So the registers and CPU cache, which is why it's expensive. The other interesting characteristic, and perhaps important, and we'll come back once we start our discussion of secondary storage, is this idea of a memory component being volatile or non-volatile, right? So a non-volatile memory component is one that doesn't lose its content when you stop supplying power to it. But a volatile memory component is one that will no longer hold the data or the program instructions when you stop supplying power to it, right? So key takeaway point here is that the vast majority of primary memory is volatile, right? I'm saying the vast majority here is because when we start making reference to things like ROM, for instance, technically speaking, it's non-volatile because it will still maintain the contents. Secondary storage obviously is non-volatile as well, right? Because it doesn't matter whether you stop supplying power to a thumb drive, for instance, USB drive, you still have contents of your data in there. So start off with so-called CPU cache, right? Again, as earlier mentioned, the idea behind CPU cache is to ensure that the execution of programs or program instructions during the fetch, decode, execute cycle is as fast as possible. Right? So rather than have the CPU make a round trip, as earlier said, you want a mechanism in place to be able to store copies of things that are regularly accessed by the CPU right on the CPU itself.
So,
Yes, sir.
there are instances when you're trying to make a bootable drive using your thumb drive. You're trying to make it bootable so that you can install one operating system. Why is it that once you burn the disk, the ISO image into the disk using Rufus, you can't use that Rufus doesn't last long. You have to reinstall the Rufus back into the disk. What happens to that program?
Yeah, I don't know how Rufus works. That's very strange. The experience I've had using different applications, like I use HI a lot, is all you have to do is once you burn that thing onto a CD, you don't have to. I don't think you'll have to redo that process all over again. It sounds like this is what you're suggesting. You do it once and that's it, right? So it's
like you're trying to use the same bootable drive to add the operating system on another device. You discover that you have to restore the Rufus again. Maybe it's just happened to me, but
no, I don't think so. No, that's not. No, but maybe you're confusing two different things here, right? So there's a there's a part where you're actually creating a bootable let's say bootable CD in this case, right? A bootable USB. And then there's a part where, so there's that process, and then there's a part where you're using what you've created, the already created bootable disk. If you create it, there's no need for you to recreate it. But if you have an ISO image on your computer right now, and you use so-called Rufus, I've never used Rufus yet, but you use Rufus to create a bootable CD. If you want to redo the whole process all over again using a different machine, then yes, you would have to install Rufus on that machine or whatever piece of software you'd want to use to create that bootable disk, so that you are able to create that bootable disk, right? But if you're wanting to just access if you want to reuse the already created bootable disk, there's no point in you installing Rufus. In fact, we've done this a couple of times. It's unfortunate that we don't have these actual lab sessions taking place. But what we normally do is when we are conducting some of these lab sessions, is we'll have bootable USB drives, and then we just pass them around in class so that people just install the operating system from the bootable disk. And in fact, when you gain access to the bootable USB in this case, there is no need for you to install the piece of software that was used to create that bootable disk, because it's pointless. The disk is already bootable, right? So your computer will know that this is a bootable disk, and so it needs to load that and allow you to interact with whatever is on the bootable disk or something. So I think you're just you might be confused with the two processes: reusing an already existing bootable disk and going through the process of creating the bootable disk. Yes, you would have to reuse Rufus if you want to create a new bootable disk on a different machine. Or Etcher, if you haven't used, I do encourage you to do this. If you're one of those people who's never used, I don't know about Rufus, but Etcher, if you, I do encourage you, this is a pretty, well, I mean, there are plenty of software tools that can be used to do this, but I find Etcher to be quite useful in this regard. You probably want to look into that. I don't know about Rufus, but how do you spell Rufus? Rufus. How do you spell? Anyway.
RUFUS.
Yeah, I don't know. Okay. Yeah. Great stuff. So I think it's probably just a misrepresentation of exactly how Rufus works, maybe. Or what sort of process you're going through as you're creating a bootable disk. Good stuff. Right. So CPU cache would typically hold regularly accessed copies of program instructions and data, right? And remember, these program instructions are associated with the fetch, decode, execute cycle. So your computer knows, as it's going through those different cycles, as you're executing different instructions, there's obviously algorithms in place that will be able to detect instructions that are regularly being accessed, right? And those are the things that are cached. And obviously, very careful attention needs to be paid to this. Why? Because you have limited CPU cache, right? The typical computer will have limited CPU cache. Think for a second here, right? If you have access to 32 kilobytes of, and this is on a modern day computer, some CPU cache is much lower than this, right? It's in the bytes actually, not kilobytes. So if you have access to just to explain this a little bit, just help contextualize things here. Just imagine this is an unusual case where my machine has separate CPU caches for data and instructions, L1D, L1I, right? But just showcase something here. You have ODI, right? L1I, and I have 32 kilobytes, right? 32 kilobytes, which is essentially nothing more than 2,368 bytes. Now, there's something interesting here to think about. Number one, it's and we haven't started this discussion yet, but once we start our discussion of MIPS, what you will realize is that MIPS, right? MIPS instructions are 32 bits in size, right? A single MIPS instruction, right? One instruction is 32 bits in size, right? Now, remember that we said 8 bits will make up 1 byte, right? So the 2 bits will essentially mean that you have 4 bytes, right? Because a single MIPS instruction is 4 bytes in size, right? What we are saying, 4 bytes in size, what we are saying is that we can hold my machine, right? In level 1 cache, my machine can hold at any given point in time 8,192 instructions on cache, right? So I don't know if this is making sense, because you can only hold this many instructions at any given point in time. And just bear with me, think of my L1I cache here. My L1I cache can only hold, at any given point in time, it can only cache 8,192 instructions. But remember that my machine right now is executing so many different things here. I have a broad spectrum of applications open. I have my my Explorer here, right? My file Explorer here, right? Dolphin, I have three instances of Chrome open. I have two instances of one instance, I guess the other one is just full screen. I have one instance of Ocular open. But in all these different instances, well, I have LibreOffice Calc open, but in all these different instances, all of these things are loaded into RAM and they're being executed to a certain extent. Right? The execution is so fast and there are thousands of instructions being executed at a given point in time. So CPU cache is there to hold the things that are being regularly accessed as I'm interacting with these applications. How this is making sense here. Same goes for data, really. When you're dealing with, like in my case here, when you're dealing with L1D cache, right? In the case of LD1 cache here, what I'm saying is that the data that is being manipulated can only be, this much of it can only be cached in my L1D cache on the CPU. All right, all this is making sense here. Usually a bit of misrepresentation of what's happening behind the scenes. And I know it can be, maybe, I don't know if you're sitting there and you're thinking, oh, but 8,182 is a lot of instructions. No, it's not actually. It's not because, I hope we'll be able to find this, but it's not because if you look up, let's say total number of instructions, Microsoft Windows 10, I guess. I don't know if we can. I'm trying to look up program instructions, total program instructions, Chrome. I don't know, I was trying to give you an idea here. And I don't want to use lines of code here. I want to use specific number of, maybe we can use lines of code actually. Total lines of code, Windows. How many lines of code, Windows 10? I hope we find this. Boom, there you go. Now here's the thing, right? If you look at, now I don't know where this is coming from here, Windows 10 lines of code or something. Look at this, if you're saying your Windows 10, and this is, don't quote me on this one, I'm not saying this is the case here, but if you have 50 million lines of code associated with Windows 10, when you do it, it doesn't necessarily mean that these 50 million lines of code will translate to 50 million machine code instructions. No, this is 50 million lines of code of a high-level programming language, right? I think. And so with that being said, what you expect is slightly more, maybe significantly more machine code instructions that are equivalent to these 50 million lines of code. But in fact, even if we were to say these 50 million lines of code is equivalent of the number of machine code instructions, if you compare these 50 million lines of code with my L1I cache, which can only cache 8,192 instructions, you notice that what is being cached here is just a fraction of those 50 million lines of code. 1, 2, 3, 1, 2, 3, right? You can, I guess, just 100. Let's look at. What we are saying is that my L1I cache, my level 1 cache can only cache 0.02% of the instructions associated with just one example application, Windows 10. Right? I hope this makes sense here. But bottom line here is that there are heuristics in place, algorithms in place that are able to figure out exactly what is being frequently accessed, so that the correct instructions are actually cached. And again, this is more to do with efficiency of the CPU. The CPU is much more efficient if it can execute instructions that have been cached on the chip itself, rather than make the long and tedious journey of going to main memory, accessing the instruction, or making a request to access the instruction, and then ferrying the data back to the CPU for execution. Rather than do this, what the CPU will do is it will just go to cache and get what it's looking for, right? So it's to do with the round trip here. And the fact that RAM, right, this memory component is much slower than the cache, or the component that the technology that's used to manufacture cache, right? So there's different things here. The round trip, latency associated with this round trip, and the throughput associated with the memory component, because this is much faster than this, because it's located much closer to the CPU is able to execute this at a much faster rate. And again, the other thing here about this execution of instructions is that if you were to compare it, like if you would compare it using one instruction, you notice that the difference wouldn't really be that much. But it turns out that when you look at it from a bigger picture, the millions of instructions that are being executed at a given point in time, cumulatively, it becomes important that you actually access things direct from the cache itself. Don't know if that's making sense here.
So,
Yes.
so is it the mandate that every sort of data or instruction that the CPU requires is going to be found in cache, or sometimes it's not going to be found in cache, it has to go to the RAM instead?
No, but it's not always, and it's not always because cache is limited, right? You have a limited amount of cache to work with. So some things that you might want to access might not be in cache. Like, so for example, right? I'm busy running a whole bunch of applications here. If I suddenly just decide to open some very obscure application that I rarely even use, I think I don't use IntelliJ. If I try to run this application, right? This IDE here, I run it here. The CPU will not be able to find any program instructions associated with this piece of software. And so what it will have to do is it will have to go to main memory, to RAM, to start executing this program, because I rarely use this program. So the answer is no, it's not always that the CPU will find what it's looking for in cache. It depends on whether you've been regularly using that piece of software or not. And this is a memory hog. I'll just exit it. Great questions. Thanks for that. Good stuff. So it turns out that caching itself, right? There are usually different so-called levels. I guess we can look at this as being different types of cache that are there, right? Cache comes in different levels. So you have level 1, level 2, and level 3 cache. And usually these differences in the levels is more to do with where they're actually located. In certain machines, you probably just have I think level 1 and level 2. Let me just quickly check. Or let me pause here. Because I always use my computers as examples. These are relatively modern computers, right? The ones that I have manufactured like within the last 5 years or something, 3-5 years or something. But let me see if I can. Let me see if I can just quickly give an example of a computer that is relatively old. I hope they haven't upgraded this, please. What you notice is that some machines will typically only have 2 levels of cache. Right? This is a bad example as well. Oh my goodness, I don't think I have access to this. It's so sad that I don't have an example of a computer that has pretty much yes, thank you. If you look at this, no level 3 cache, right? So it's not always that you have level 1, level 2, and level 3. The distinction that's there really is that the vast majority of computers will typically have, at least those that have been manufactured, generation number 4, I guess. From generation number 4, you typically have 2 types of caches, right? And this is more to do with multi-core processors, really. So the idea behind the different levels of cache is you have certain levels of cache that are accessible by the individual cores associated with the CPU, and certain types of caches that are shared by the cores that are associated with that CPU. So if you have a quad core processor, for instance, let me see here, this is a dual core, quad core, number of sockets, oh, single core, sadly. Okay, that's quite sad. So the idea would be that you have level 1 caches associated with the individual cores, and then you have level 2, which is shared by the by all the cores associated with the computer itself, associated with the CPU. Right. So this visual representation here shows you exactly what this is all about. So level 1 will typically be located on the it's number 1, it's located on the CPU itself. Then also it's usually associated to the individual cores. It generally, for the most part, it operates at the same frequency as the CPU. So if you're saying the throughput of the CPU is, let's say, 2 gigahertz, then level 1 cache will operate at the same frequency, which is a good thing, right? And then you have so-called external cache, and in this case is being called external cache because it's shared ideally. These notes, we're making reference to level 2 cache as being shared here. So it's also typically be located on the CPU cache, but then it's shared by the various cores. And I'm sorry about the fact that we've actually annotated it here or highlighted it as being located on separate cores, but the notes speak to the fact that the level 2 cache would typically be, it will be on the CPU itself, but it will be shared by the various cores. So the idea really behind this sort of caching, CPU caching, is that seeing as you're different levels of cache, when you're dealing with level 2 cache, the idea is if the CPU cannot find what it's looking for in level 1 cache, it will check in the next level, which is level 2 cache, right? And hopefully it will find what it's looking for. If it does, then that is good because of the fact that your level 2 cache is stored on the CPU, it's going to be orders of magnitude faster than if the CPU was to go and make a round trip to main memory, right? To RAM in this case, or ROM. If it doesn't find what it's looking for in level 2 cache, then assuming you don't have level 3 cache, it will go to RAM, right? If you have level 3 cache, then it will check in the level 3 cache here, right? Which we are saying is shared cache here. So a couple of interesting things that are happening here, right? The fact that access by the CPU to program instructions and data is ordered in a way, right? So access begins with the much faster memory components, registers, right? CPU cache, and in fact, more specifically, different levels of CPU cache, then RAM, right? So this whole thing that's happening here, access to program instructions and data in the various levels of caches, brings us to interesting discussion linked to so-called cache hits and cache misses, right? And it's to do with what typically happens as the CPU is wanting to gain access to specific types of program instructions or data. So in terms of the cache hit here, what we're saying is that the cache hit would typically happen when the CPU is able to find what it's looking for, either data or instructions, in either one of the caches, right? So either level 1, level 2, or level 3. So CPU makes a request to certain program instructions. First will check if what it's looking for is in either, if it's in level 1 cache. If not, it checks in level 2 cache. If not, it checks in level 3 cache. As it's checking the various levels, if it checks in level 1 cache and it finds what it's looking for, it's a cache hit. If it checks in level 1 cache, it doesn't find what it's looking for, and then goes on to check in level 2 cache, it finds what it's looking for, it's a cache hit. If it checks in level 1, not there, checks in level 2, doesn't find what it's looking for, checks in level 3 and finds what it's looking for, then that's a cache hit as well, right? Data is going to be sent back to the CPU register for execution. On the other hand, if the CPU makes a request to gain access to program instructions or data, and is unable to find what it's looking for in either of the caches that you have, right? Can't find what it's looking for here, then it's a cache miss, right? It's a miss because what that means is the CPU is going to have to go to main memory to get what it's looking for. Again, everything is centered around efficiency. Efficiency is king, right? Okay, just a few examples here showcasing some, I hope I have more examples. Oh, I do. So some screenshots of different computers, right? So this is a microcomputer.
Oh, Dr. Lighton,
Yes, sir.
just there on the same cache, you have said that level 1 cache will be a little bit much, it will be small but yet fast. Level 2 cache will be a little bit large but it will be slower. And then you referenced the fastness of the level 1 cache due to the fact that it's on the CPU itself. If the CPU is maybe about 2.5 gigahertz, billions of instructions per second, then that's how also the first cache in terms of its speed will be. Now the level 2 cache, they are also located on the CPU. If you bring up that slide where you are indicating, together with the level 3 cache as well, they are also located on the CPU regardless of their size. Then does it mean that as the size begin to increase when they are being manufactured, the slowness is with regard to the technology, or rather the distance between, or rather there's a little bit of distance between the level 1 cache which is on the CPU with maybe the level 2 cache which is also on the CPU, or the slowness as they increase in size, even the technology they're implemented with is the one which causes them to be slow even though they are found on the CPU as well.
Yeah, well, so it could be, it's mostly due to the technology, right, and the speed. Think about this for a second, right? So the amount of, I'm trying to think of it in terms of cash here, but as in cost, but when these engineers are designing these computers, right, cost is extremely important, because these computer manufacturers, these hardware manufacturers are interested in making money, right? This is what they're interested in. It's all about money here. And so in as much as you might have, and I'm sure they are there, right? You might have computers where the speed at which level 1 cache and level 2 cache operate is more or less the same as the CPU. But what that means is that the level 2 cache is going to be, or level 3 cache here, it's going to mean that that machine is going to be slightly more expensive. Why? Because typically your shared cache is going to be slightly larger than the cache that is associated with the individual cores here, meaning that it's more money, right? But if you want to reduce the cost, the manufacturing cost, then what you do is you use a slightly cheaper technology, right? So you're using a slightly cheaper technology so that in as much as you have higher capacity level 2 cache, but the amount of money that you're spending on manufacturing that particular computer is going to be, it's going to be a reasonable cost, right? So it's to do with the technology for the most part, but that doesn't necessarily mean that you can't have a computer that is designed in such a way that the same technology was used for level 1 and level 2 cache. So typically they're operating at the same speed, essentially. Just like we said when we are looking at primary memory, right? It's possible that you can use the same type of technology that is used to, well, in this case, but hypothetically speaking, same type of technology. Actually, it's possible that you can use, as far as RAM is concerned, you can use the same type of technology, SRAM, for RAM, right? Same type of technology that is used for CPU cache. But the thing is, you end up with a expensive computer, right? Question you're asking yourself as a manufacturer is, how many people are going to manage to purchase this? It will have to be slightly more expensive, yeah? It makes zero business sense for you to do that. So yes, the answer is yes, it is more to do with the technology actually, or at least in part.
Yeah, all right, thank you, sir.
Yeah. What would be interesting is, I don't know if you guys can share some details to do with, remember that exercise we're doing with, one of the lab exercises we're doing with your computers? What I want you to do is, it's always nice to, try and put to practice some of these things, especially if they're more theoretical things. You want to poke around and try and see if you can better understand this. One of the things that we asked you is to look at you were using certain funny tools like CPU, was that CPU info and CPU X and CPU Z? If you go back to some of those utility software tools, what you will notice is that some of them will actually give you an idea of details to do with CPU cache, for instance, right? So it would be nice if you could do that. Hopefully that will make you better understand some of these things we are looking at here. And as I'm talking to you here, I'm trying to see if I can if I can find this information using CPU info. Probably not. If not, I'm sure there are other utility tools that you can hunt for out there to try and see if you can decide it's not there. Okay, that's fine. Right. So, but you notice that obviously when you're dealing with a microcomputer, the size of the caches might be somewhat different, especially for the shared cache, right? Level 3 cache in this case. I don't know if you can notice the fact that if you look at this microcomputer here, which is a Probo, really old machine, almost a decade old, I guess, and you compare it with a server computer system here, right? You notice that the shared cache is slightly larger, right? I don't know if you can see this. Compare this with, and in fact, I could look at a more recent machine here, do a comparison, and maybe that'd be much better. So my Lenovo IdeaPad 320 has observe here, right? It has 32 kilobytes of. Let's look at this. This should be interesting. An interesting exercise here. So let's look at level 1 cache, level 2 cache, level 3 cache, and then let's look at microcomputer. Let's look at a server computer, right? What you will notice is that, and I wanted to, and I know this is like one of those horrible comparisons here, but this has 32 by 1024, the 1 cache, the microcomputer here, right? Also has, excuse me, it has 256 KB, so which is 256 by 1024 bytes of level 2 cache, and level 3 cache of 8192, so it's 8192 times 1024. So I have this much bytes of available level 3 cache, which is the shared cache. But if I'm to compare this with a server computer system, what you notice is the level 1 cache. This is a server, by the way, server computer system. You notice that I have 8 cores here, and I don't know what other things you can use. If you look at the maximum, this is a thing here. Maximum is 2 gigahertz here. Yeah, this is an old machine, a horrible example, but it's probably an old machine. Can I exaggerate this? Goodness. Horrible example, right? Can I check for something else? Oh my goodness, hpc.zambia.zm. I want us to just do, I want us to latch on to some earlier topics that we've discussed. Specifically, categories of computers, right? And I don't want us to do a comparison with an old or an ancient server computer system and compare it with a more modern microcomputer, because it will turn out that the comparison will be a bit flawed here. And I'm guessing you've already seen the flaw in the comparison, right? If you look at my, I'm on my machine right now, right? If you look at this, if you look at my Lenovo IdeaPad, you notice that the maximum CPU speed here is 4 gigahertz, right? 4,000 megahertz. And so if I'm to compare this with a server computer system, I'm on a remote server computer system here, right? I don't know if you can see this, but it's a remote server computer system here, clearly, right? If you look at the IP address. If you compare this with maximum CPU speed here is 2.4 gigahertz, right? So it's a bit flawed here. So I was hoping maybe we could do a comparison with, I hope, the HPC servers that I have access to at Zambia. I hope these, am I using the correct credentials here? I hope I am, but let me just check here. I hope so. I don't know. I'm not even sure if I'm using the correct server details, but maybe I am. I hope I am. No, probably not. It's I think it's strange. I don't know, but okay, please. And I know this is running. I think it's running Red Hat or something. I hope I'll be able to. And you notice I'm not on the machine here. I'm on the remote server, my computer system at host name. I don't know if you can see this. Anyway, yeah, I'm on a remote machine. So if I CPU or something, what you notice is that I hope the maximum speed here is. Yeah, but still. But anyway, so what you notice is that for server computer system, right? The sizes. This is, by the way, this is a high performance computing infrastructure we're looking at here. But the sizes of these caches is somewhat different, right? The server computer systems typically have significantly higher capacity insofar as cache size is concerned. And this makes sense. If you think about this from the perspective of what server computer systems are used for. Who's a website, thousands of hits at any given point in time, a lot of activity happening there, right? Reliability, right? So there'll be a lot more activity happening on a server computer system as compared to a microcomputer system, like your phone, right? Look at your phone and it's just you, right? Who else is accessing that phone? Just you. Look at your laptop, it's just you. Granted, I mean, if you're a power user, you might be doing a whole range of things there. I'm going to pause here to find out if I'm talking to myself. I don't know if I've lost connection. Am I there?
Yeah, yes, sir. Yes,
okay.
Yes, you are.
Okay. Yeah, so if you do a comparison, and go back to the comparison here, and so we're going to go to maybe a more modest server computer, right? Nightmare. You notice here, right? Level 1 cache, it also has LD, LI cache also. So same size, the 2 kilobytes. Just multiply this with that. Level 2 cache, 256, I guess same size, 256. But what you'll notice is that the difference is in the shared cache. Shared cache makes sense, right? 122.288 makes sense. 122.288. Why? Activity. Activity, gentlemen. What the hell am I doing? 122.88. 122.88 times 1024. Right? Differences. Server minus microcomputer. Right? Difference in terms of kilobytes. Right? You notice that the difference in terms of megabytes. You notice that, oh, it's not there. So just use kilobytes. You will notice here that, I wonder why this is not there by 1024. 4. So it's a difference of about 4 megabytes in terms of like level 3 cache associated with server computer systems and microcomputer systems. Makes sense. Why? Level 3 cache is shared, ladies and gentlemen, right? Level 1 cache is not, right? It's associated to individual cores linked to that particular computer system. Anyway, key takeaway point here is that, what you're caching are individual instructions and data. Just small little things here. Like if you think of instructions being cached in terms of the bytes, right? And of course, the size of the byte is contextually depends on the implementation of the hardware itself. Our case example, once we start looking at the computer architecture component of the course, is going to be the MIPS instruction set architecture. And for MIPS, instructions are 32 bits in size, 4 bytes, right? So make sure what you're caching in these sizes here, the 2 kilobytes here is, it will be like your individual 4-byte long instructions, right? What we're explaining in this slide really is just the idea of the hit and miss really, trying to highlight the workflow that we've already looked at. What will typically happen is CPU is executing instructions, right? Fetch, decode, execute. Fetch, decode, execute. Fetch is what? Reference to memory, if you remember. You go and fetch from main memory. And we were abstracting some of these things, again, we're abstracting some of these things when we're saying we fetch from main memory. But in actual fact, particularly speaking, cache is main memory, it's primary memory. But in actual fact, it doesn't mean that all the time the CPU goes to fetch the instructions from RAM. It is possible that it will find what it's looking for in cache, right? So CPU initially check the first allocation, which is cache, the location, the memory component, which is much closer to the proximity to the CPU itself, which is cache, before it cascades to go to RAM, right? So the cascading really is like, it's unwinding kind of, right? Level 1, level 2, level 3, main memory or something, or registers level 1, level 2, level 3, main memory. So again, this is more to do with efficiency here. So you check first in cache, is what I'm looking for in cache. Then if it finds what it's looking for, it does it. Now, also look at this, right? I'm sorry that the block diagram here is a bit misleading here. Maybe we shall flip it over. So imagine that this is RAM and then you have secondary storage here, right? But maybe it would have been better if it was top down or something. I don't know. Secondary storage. So what we are saying is you have your CPU somewhere, right? CPU, it will start checking the cache first. Can't find what it's looking for, it will have to go through the buses here and go to main memory, where it will find what it's looking for, right? Anyway, are there cases where you think it won't find what it's looking for?
In case of
in cases where it won't find what it's looking for in main memory, would there be a case where the CPU will never find what it's looking for in main memory?
Yes.
How is that possible? Why would it be executing instructions in the first place if it won't find what it's looking for in main memory?
Oh, if we relate to this to the input-output subsystem, maybe if it finds that the data that an I/O had to provide through a peripheral's request, if it has not yet been provided, meaning to be looping, checking, right? It will be looping.
Yeah, no,
checking.
but at that point, it's not really accessing data, right? Remember, the sequence of events is a signal first, right? Depending on which technique you're looking at, really. Like if you're talking about polling here, what you're saying is there'll be a subroutine, right? Subroutine, which is why it's called programmed I/O, checks. Does this data have what I want? Transmission of data is only initiated once there's a go-ahead to say, yes, I have something that needs action in here. So when what we're talking about here by checking here is to check if what the data transmission, this checking is to do with data transmission. Because what the CPU is looking for here when it's checking in cache is data, right? Program instructions or data. So we are conflating two different things here. signaling, which is control bus, right? And data bus, right? Two different things. But this is good stuff, I guess. But also, just to kind of wrap up on cache here, I guess. Then let me see if we can, and then we'll have RAM next time we meet. Just kind of wrap up on cache here. Again, you should look at cache still from the perspective of the memory hierarchy, right? So this idea that obviously the different level 1 caches will have, for the most part, in certain instances, I guess, will have varying speeds, varying capacity, right? Capacity will be different. The throughput is going to be different. And because capacity and efficiency, right, is different, then the cost is going to be different. Something that has a much higher throughput, logically speaking, should be slightly more expensive. It's much faster. Well, go and check the prices for, I don't know if mom and dad have a Ferrari or something at home, but you should ask them how much it was and then compare it with a Corolla or something, or a bicycle, right? I have a bicycle myself, which is much cheaper than a vehicle, right? Throughput. Again, so you can visualize this from the so-called memory hierarchy or pyramid. So your level 1 cache should be up at the top there, right? Your registers, level 1 cache at the top, and then your level 2, level 3 caches will be somewhere at the bottom here. All right. So I'm gonna pause here, right? And in closing, what you will soon see here is that, again, this will come up a lot. This must sink in. As we're looking at the different memory components here, the aspects that we introduced when we first started our discussion of main memory are going to behave in a way that we've already explicitly stated. Size, efficiency or throughput, and cost, these will typically change. Are there any questions, ladies and gentlemen? I'm looking at, it's a Friday here, 9:16. I think we'll just have to quit a day or quit a morning. I'll see you when you see me, unless if there are any questions. I don't know if I'm even online now. Are there any questions?
There's a question in the chat.
Yeah, the problem with the chat here is scrolling through the chat, I see there are 48 messages. It's a bit, where's the question here? I don't know what, is this a question? What is that? If you know it, I don't know what this means. Is this a question you're talking about? This is not a question.
Yeah. The last message.
Which, or even this? So does it mean the reason why the L2 cache is slow is because of the distance? Well, it's a bit of both, right? So it's the latency, right? The proximity, because it's probably not, actually technically speaking, it's on the same CPU chip. It's based on the design. The difference is in the technology that is used to manufacture these components, right? Which is why you can get away with having more level 2 cache. Look at this. Yeah, all the different case study machines we're looking at, server computers and whatnot, they have slightly more level 2 cache than level 1 cache. So it is in part because of proximity, right? So if you look at this example, for instance, it only has level 1 and level 2, right? This is shared cache. This, on the other hand, is cache that is associated with individual cores, I guess. What that means is that because they're associated with individual cores, they're on the cores themselves. So they're much closer to where the execution actually takes place. So yes, to a certain extent, that is true. Yes. Any other questions? I'm sorry that I can't sit through all these, the chat. It would be nice if you could use,
sir, I've got a question.
Peripheral.
Sir.
Yes, sir. Yes, sir. I thought somebody had a question. I don't know what happened there, but.
Okay, so how soon can you make this meeting available?
Yeah, this is a bit. I've been a bit busy. So uploading these things is what I was trying to do with the previous one is I need to splice it up because of the discussion to do with lecture series number 9 and the discussion to do with lecture series number 11. And video editing, I hate that, right? It's time consuming. It is time consuming. So I would try as much as possible to make this available maybe by tomorrow or something. I have a couple of other classes today, so uploading and adding the details onto Moodle, that's a time-consuming task. But I'll try as much as possible to make them available very, very soon. Any other questions?
All right. And sir, how soon are we going to receive our test results?
Yeah,
I mentioned this
that I mentioned. Sorry, you what?
I checked through the review of the same test, and then a few questions were marked already, and others were not.
Yeah, the things that were marked were probably automatically graded, right? I mentioned that, and I hope this will sink in now. The marking is we don't know when the marking is going to take place. I don't have a tutor in this course to assist me with that. We are busy with other things right now, IDA courses, exams, the process. But I'll try and ensure that we make them available as soon as possible. I'm not sure when. Hopefully soon, though. I don't know. Hopefully soon. Yeah, sorry about that. Hopefully soon. It's a bit. Guys, I see it's 9:21. I have to get out of here. Thanks a lot, and see you when you see me. What about quiz? What are you talking about? Come on. We are now talking about things that don't make sense. Okay, thanks a lot. Have fun over the weekend and stay safe. Bye-bye. Thanks. Stay home.
Same, sir.
Guys, what's happening? Huh?
So guys, this week there is no quiz.
I guess.
Mr. Nito, he always sends a notification that we're going to have a quiz. So about quizzes, you don't even have to worry about that. You just do your part, and when he sends the notification,
worry about
It's random.
Light on dice upon random. So he always tells us in advance, that's the good part.
Okay. What about the discussion? What?
Yeah, we should have a discussion today according to I think Paul should be looking into that, because if there are some past paper questions, he should be the one presenting today. So that is if we have a meeting. Anyways, people you continue asking in the discussion group so that we see the response to if these people are prepared.
All right. Mr. Patrick, can you kindly resend those links regarding the IO subsystem? I lost everything when I reset my PC. Oh, when I reset my phone. Sorry, my phone.
I'll check if they are still available in the group. Then if they're not available, then maybe I'll try also to. I think I remember what I searched in the Google engine, so I'll try to send it. Anyways, I'll send if I find them. Okay.
Oh, and then when likely can we be able to buy the stickers? Because my PC is becoming wretched by the day.
It's the same issue I told you. Like for my case, I bought the laptop, and then the date the seller told me that it has been delivered to the people who have to bring the laptop here in Zambia was on 24th. That was 24th of July. And since then
it arrived on the 11th.
Yeah, 24th of July, and today it's on the 14th of August. I don't know if you count, it's about 3 weeks transition into a month, So I sent a message to them. They were telling me that this consignment will come over the weekend. So you will receive a notification maybe this coming Monday. And Wallace, the estimation date has already passed. So the way things are taking long and everything. And by the way, when I checked the stickers, the last country available with those stickers in a which are very affordable, it's coming from China. And if we are to buy them from China, my friend, I don't you probably will receive them in December.
So it's better set up for those skins, eh? The
Uh,
PC skins.
which ones?
The skins.
Oh, the skin. You want the skins, not the stickers.
I want both. I was looking for both for either, but whichever comes first is the one I'll get.
Oh, okay. Anyway, we'll continue checking. We'll continue checking. And
Right, but so far, how's Kitwe?
Kit, we are trying. We are
No,
surviving.
yeah.
We are surviving here at least, my friend.
Yeah,
Then
then I'll keep in touch. But the fact that I've been missing meetings for for last week and this week. Oh, for this week and the one we had the last time we closed off the discussion for IO subsystem.
yes.
So I kind of like need to arrange everything. And let's hope we don't have a meeting for 10:20. Because if we do, oh, by the way, how many did you get for 10:20? Your assignment?
It was like he gave me 60. Yeah, he gave me 60%. He said that I did not explain. I don't know what details he wanted, but there are things he told me that I should go through. So I'll try going through those in terms of
Oh, yeah.
the creation and dissemination of information.
He gave me a 70 and said, I also need to talk about the bad side of what technology had done.
And yeah, that's the good part. We just have to go through.
Oh,
At least when
the
there are
recording is
feedback
still going
comments like
on.
those from the yes, yes, brother.